okay, that improve their performance P, at some task with experience. Okay, machine learning is a well-defined learning task that is given by these three, let's say, parameters P, T, and E. Okay, like in the machine learning task, it should have all these three. Performance measure on இருக்கணும், there should be some task, and there should be an experience. I'll be going on deep into what these three are in further slides, but let's look at traditional programming versus ML or machine learning. Okay, traditional programming, what you would have done is there would be rules, you have data, you program in such a way that you extract certain answers from the data. Okay, those rules are the code that you write. But in the machine learning case, you have data with you. Again, I'll be coming on to what data is. You already know what the output is. You combine these two and get the rules. Okay. So whenever a new data point comes to you, what you want is the answer. Uh, let's say I take a test for cancer. Okay. What I want to do here is you have images of cancer tissue, like from all the previous patients. You know whether they have cancer or not. Okay. The machine learning case, you combine these two and look at certain patterns. Like I'll say if this particular pattern is there is in this image, I would say whether that particular patient has cancer or not. This is one type of a learning paradigm, and this is it is heavily reliant on data. Okay, whatever amount of data we have, that much good will be the performance. Whereas programming relies on logic. Programming வந்துட்டு whatever you write, that's what it uses the data and gives you answers. But machine learning, it learns on its own from data. This is the difference between traditional programming and machine learning. And when to use machine learning? Okay, ML can be used when human expertise does not exist. Marsla, we don't know what environment we are navigating. Okay, we don't have any idea how the environment there is and what we want to do. Okay, so that's where human expertise is not there. We learn from existing data. Number previous ஏதாச்சும் satellite mission somewhere we could have sent a device. You use that, get data from that, and learn those rules so that whenever we try to train a newer robot, it can navigate on Mars. Okay? Then the next area is humans when humans can't explain their expertise. One is speech recognition. Uh, Typically, what we do is whoever we are close with, we can recognize their voice or something. But if you give a random voice, we can't recognize it, right? So that's why we need to, we don't know how we recognize their voice. So that's where we can't explain their expertise. But machine learning, what it can do is it can go through all existing voices, and whenever a newer voice comes into picture, they can recognize whose voice it is. Okay. And then the third aspect is personalized medicine. Okay. Uh, right now in medicine, the case is ஒரு ட்ரக் வந்துட்டு சில பேருக்கு ஒர்க் ஆகலாம், சில பேருக்கு ஒர்க் ஆகாம இருக்கலாம். பர்சனலைஸ் மெடிசன் இந்த கேஸ்ல வந்துட்டு we need to find out எந்த பேஷண்ட்டுக்கு which particular drug can be used. Okay, that's what personalized medicine is. And the fourth aspect is when there is huge amounts of data. We humans can't go through lots of data and come at a conclusion. So that's why we need these machine learning models. Let's say in the example of chat gpt, it has been trained on huge amounts of data that we can't even imagine. Okay, and then it comes to a conclusion based on patterns in the data. Okay, So these are the cases where we can use machine learning, but I would suggest don't try to use ML everywhere. We have we have rules defined for building a calculator. Okay, so we don't need to build a machine learning system for a calculator. You don't need to collect data. You don't need to train a model. Just for building this calculator where logic have been previously defined. You don't need to use ML. Okay? This is one of the classic machine learning tasks that you can see everywhere on the internet. This is called the MNIST handwritten digits dataset. Each one's handwriting, you know, is a little bit different. Uh, when looking at this, I can't say for sure whether it's a two or not. Okay, but we can train a model that can look at all different variations of two. Okay, in the dataset, and then when we give a newer instant, either could I can't know for sure if it's an 8 or 0. So the model can actually, predict what digit it is. Okay, based on this particular handwriting. Uh, so people whoever wants to start with machine learning often go through this data set, okay, and then try different models, try to increase the accuracy of the model. Again, accuracy na evlo correct இருக்கு the model prediction. If I give this image and it predicts it as 0, then my machine learning model is fine. If it predicts, if the gives an answer as 1, that is an incorrect answer, and I want the model to know that it's incorrect and then try to rectify it. This is what machine learning typically involves. And again, if you want to look at more ML tasks, one is again facial recognition, one is speech, one more is speech recognition, recognizing patterns. Then one more is medical images, like I said in the case of cancer. Then you don't need to recognize pattern; you can also generate. Yeah. I think all of you must have gone through search to the internet, and you can actually generate images or motion sequences. Okay, you can also generate music, you can generate videos. You just have to define what you want in the image, what you want in the video, and the machine learning model can actually do it. Okay, then one more is recognizing anomalies. Anomalies now some unusual thing that is happening. Credit card transactions, it can go through and see the transaction if it's actually done by you or is it some scam or fraud or something. And unusual sensor readings in nuclear power plant that might be very critical. I want you all to answer this question: ML for prediction. Okay, how can we use ML for prediction? Prediction now, I will look at what all data I have in the past and how can I do a prediction in the future. Past data வச்சுட்டு how can I predict the future? So any examples you can think of? You can use the chat box, you can speak up, so anything would be fine. Any examples, anything you can think of. கரெக்டா இருக்கணும்னு அவசியம் இல்லை. எனி எக்ஸாம்பிள். நான் சொல்றது கேக்குதா? ஹலோ, மை ஆடிபிள்? ஏதாச்சும் டவுட் இருந்தாலும் கேட்கலாம். இவ்வளவு தூரம் எக்ஸ்பிளைன் பண்றது புரியல. Yeah, that's also correct. So sensor readings வச்சுக்கிட்டு you can predict in the future. லெட்ஸ் சே இப்போ ஃப்ளட் வரப்போதா இல்லையா அப்படின்னு வந்துட்டு கரண்ட் வெதர் கண்டிஷன்ஸ் வச்சுட்டு ப்ரெடிக்ட் பண்றது. யா, தட் இஸ் ஒன் கைண்ட் ஆஃப் ப்ரெடிக்ஷன். எனி அதர் எக்ஸாம்பிள்ஸ்? நைஸ் ஒன். நெக்ஸ்ட், இதே மாதிரி எனி அதர் திங்ஸ் யூ கேன் திங்க் ஆஃப்? Yeah, earthquake prediction, stock price prediction. Yeah, that is one more good thing. Yeah, stock price prediction based on previous trends. You predict what the stock price will be. Yeah, good examples. Yeah. Any doubt still here? இது சொன்னது எல்லாம் புரிஞ்சுதா? Can I go move on? Hmm. Yeah. Okay. Next. So successful applications of ML. Chat GPT யாரெல்லாம் யூஸ் பண்ணிருக்கீங்க? இல்ல தெரியுமா? தெரியுமா chat GPT என்னன்னு தெரியுமா? யாரெல்லாம் யூஸ் பண்ணிருக்கீங்க? ஐ திங்க் இதுல ரியாக்ட் பண்ணலாம்னு நினைக்கிறேன். எஸ். Okay, good. Uh, so can anyone explain what it does? ChatGPT. How do you use it? How do you use ChatGPT? எதுக்காக ChatGPT யூஸ் பண்றீங்க? அசைன்மெண்ட் எழுதுறதுக்கா? இல்ல ஜென்ரலா கோடிங் ஏதாச்சும் தெரியலன்னு கேட்கறதுக்கா? எனி யூஸ் கேஸ்? அதான், just why do you use ChatGPT for? Is it good? Do you know how it's trained? Hmm. Yeah, to solve errors in code. Yeah, அதெல்லாம் nice use cases. Good. And இது எல்லாத்துக்கும் பின்னாடி இருக்கிறது machine learning தான். Okay. I think by the end you won't be able to learn how to train ChatGPT, how to make your own ChatGPT. But I just wanted you to know that machine learning is the basic principle behind it. Okay. Then one more successful application: autonomous cars. Okay. Autonomous cars. These are, this is going to be the future where you don't need to drive. The car will move move on its own. Okay. And these are, I would say, two successful applications of ML. Any other successful applications you can think of where you have interacted with AI, machine learning, any other successful application? Anything you can think of. நீங்க டெய்லியும் பண்ற கூகுள் சர்ச் கூட வந்துட்டு மிஷின் லேர்னிங் பேஸ்ட் தான். கூகுள் சர்ச், then you interact with Google Assistant or Siri, that is also based on machine learning. Yeah, Google Bard, that is also machine learning. So recently there was something called Gemini from Google, again beating ChatGPT and everything. Yeah, these are all successful applications of ML. And yeah, And so again, moving on from the applications, okay, before we move on to build an ML system, we want to define what is P, what is T, and what is E. We want to improve on task T with respect to a performance metric T based on experience. Experience here na data set. Okay. Let's look at some examples. Task வந்துட்டு playing chess. Okay. How do we evaluate how good it is? Number of games won against a player. நிறைய games win பண்ணுச்சுன்னா the better is the model. Okay. And experience வந்துட்டு play practice games against system. The machine learning model can play practice games against itself and then keep on improving. Okay. This is one learning task. The second one is recognizing handwritten words, like I showed previously. And how do you evaluate it? What is the performance metric P here? That is the percentage of words correctly classified. Okay. And the experience here is dataset containing human labeled words. Dataset containing human labeled words. Now, previously, a human has gone through most of the images and he has labeled it, whether it's a 0 or 1. Okay. இந்த மாதிரி நிறைய label data sets இருக்கு. So let's take the task of email spam classification. Okay. I want to know whether the email I'm getting is actually related to me or it's just a spam email. Okay. Uh, yeah. Can anyone define what will the performance metric be and what will be the experience? What's the performance metric? How do I know that machine learning model is actually good for me? The answers. Mhm. It's easy. Just look at the previous task and you can actually guess what will be P and E here. Look at this and answer this. I don't see any answers. Okay. Performance metric here will be percentage of emails correctly classified. Okay. More the number of emails correctly classified, better my model is. Okay. And experience will be a data set containing human labeled emails. So previously, an expert human has gone through many set of emails and he has actually labeled whether that email is related or spam. Okay. So any machine learning system you design must have this learning task where you define what the task is, what will be your performance metric, and what will be your experience. Okay. Any doubts till now? Can I move on? Hello, am I audible? Okay, good. Thank you. So Machine learning, those previously I was talking about all learning tasks. Okay, these are different types of learning in ML. Okay, first one is supervised learning. Okay, you have training data with you and you have the desired outputs. Okay, the next one comes is unsupervised learning, where you have data with you alone. Let's say here in the supervised setting, you have emails, you have whether it's spam or not. So those are the labels, whether the email is spam or not spam. In the unsupervised learning case, you only have the emails with you, you don't have any labels. Okay, and what you want to do is separate based on the emails alone. I want to guess whether it's spam or not based on the given training data. The third one is semi-supervised learning. Okay, you have training data, but each email does not have, whether it's spam or not. You only have a few desired outputs. The entire training data does not have the labels. Only a few of them have the labels. Then the fourth type is reinforcement learning, where it's a trial and error based method where you get rewards from sequence of actions. Again, I'll be explaining in detail what each type of learning means. Okay. First one is supervised learning, and in that it's regression. Okay. So we have X1. This is your training data. Y is continuous. Continuous, it's not, you have real valued numbers. Okay. And you have these pairs. Each data point is associated with a label. So that's what the definition of supervised learning is. Okay. You have n data points. What we want to do here is we want to learn a function f in mathematical terms. Okay. We want to learn a function f that takes x as input and gives y as output. Okay. You take in x as input, give y as output. Okay. And if y is continuous or real value, that is a regression case. Okay, this is a simple linear regression plot I'm showing here. Okay, where x will be, number of TVs that you have, and sales will be how much TVs you have sold. Okay, based on this, I want to predict how much sales will be happening based on the number of TVs that I currently have. I want to guess how much of the TVs will be sold. Okay, this is a regression case. Can anyone, get some more examples for the regression case? Any examples? You have an input, you get an output, and whatever happens in between learning the functions and all, that's what is machine learning. Any other examples? Regression. Supervised learning, you should have pairs. You should have the input and out, both pairs. Any example? Hmm. Yeah, prediction of number of road accidents. Yeah, stock price is also regression because price is continuous. Okay, and yeah, these are good answers. Thank you. And moving on to the next case, that is supervised learning and classification. Okay. Again, as said before, in supervised learning, you have the input and output pairs with you. We want to learn a function to predict the output given an input. Okay. The only difference between regression and classification is Y is categorical. Categorical means you can only say whether Y is high, one or low, zeros or one. It should be discrete or categorical. Okay. So this is the regression case and this is the classification case. Uh, uh, I hope you can see the difference between the two. Any examples for classification? I've already talked about one previously. Classification. Classification, you have a fixed set of outcomes or outputs. And I've already talked about one before. The classic machine learning task, what it is. Heart disease prediction. Yes, that is also whether you have the disease or not. Okay. That is one thing. And again, the MNIST data set I was showing, the digits recognition. Okay. That is also classification. Okay. If I have only 0 to 10, okay, only those numbers handwriting I have. Okay. How many classes do you think I should predict? Like, how many classes are there? 0 to 10 numbers. How many classes should be there in the output? Okay, so it should be 11 classes. No? Like it can be 0, it can be 1, it can be 2, 3, nothing between 0 and 1. Okay, if there is something between 0 and 1, that will again turn into a regression problem. Here I have explicitly defined what my labels are. It can be 0, it can be 1, it can be 2, all the way up to 10. Okay, this is a classification task. Regression means if I have labels like 1.1, 2.5, 3.3, and everything. Okay, anything between and the number of classes are infinite, that can be my regression case. Everything is clear till now. Can I move on? Again, in the stock price prediction also, you can predict whether the stock market will crash or not. That is a classification. If you want to predict the price, that is regression. If you want to look at whether it will crash or not crash, that is your classification case. Everything depends on this output Y. Okay. And you have different machine learning algorithms to take care of different types of Y, regression and classification. We'll be talking about more of all of these in detail also. Yeah, everything fine till now? எல்லாம் புரிஞ்சுதா? Any doubt, anything you can ask. Don't think like this might be a silly question. Only. Any question is a good question. எல்லாம் புரிஞ்சுதுன்னா I can go to the next slide. Okay. I'll go on to the next slide. So this is one more. This is like a supervised learning example. This is again a different data set, the fashion feminist data set, where you have different images of fashion accessories, shoes, dress, bag. Okay. So is this classification or regression? Answer that. Yeah. Is this classification or regression? See, supervised learning for each data point or each outfit, you have the label also. Each accessory, you have the label also. Yes, it is classification. Good. Uh, can we convert this to a regression problem? Any other regression output you can think of? If it can be, if it's the height of the accessory or width of the accessory as the output, again that will turn into a regression problem. Okay, it all depends on how you want the output to be. Okay, uh, moving on to the unsupervised learning case, you don't have any labels, you don't have y at all. Okay, but you have x with you, you have all these data points with you. What I ideally want from this case is I want to know the hidden structure behind this data point, and I want to cluster into distinct groups. Okay, so here I think this is like a nice visual representation of the unsupervised learning algorithm case. Okay, so again, I don't have any labels, but using the machine learning algorithm, I can actually separate it into distinct groups or classes. This is the unsupervised learning case. Supervised learning, you have the label also associated with each data point. Here, you don't have any labels, but after applying the algorithm, you get these labels. You actually infer these labels. Okay, it's the clustering case. And one more real life example I would say is gene expression signature. I think this might be too much biology involved here, but the general idea here is we looked at different for different patients and see what is different in their genes. Okay, we look at their genetic makeup and see what makes them unique. Why someone has this specific cancer, or what genetic makeup they have, so that this increases cancer risk and so on. And here uh, I don't have any labels with me. I only have the gene expression signatures, and I want to separate them into distinct groups. That is the unsupervised learning case. And moving on to the reinforcement learning case. Uh, so reinforcement learning, what it deals with is we have a sequence of states and actions. States meaning how I perceive my current environment. Okay. Right now, if I'm sitting in a room, let my state can be where I'm sitting. Okay, which exact point or coordinate I'm sitting. Okay, the x and y coordinates based on the room. That can be my state. Action can be where I move. Okay, uh, should I move towards the right? Should I move towards the left? Should I go front or go back? Those are my actions. Okay, and accordingly, based on the action that I do, I might get some reward. Okay, the reward can be there might be some snacks far away from me based on my current action. I might go to the snack correctly, or I might not get it, so that might be a reward. And so what I ultimately want to learn here is something called a policy. Okay, mapping from states to action. I want to know the best possible way to go to that snack. Okay, that's what reinforcement learning deals with. Other examples here can be balancing a pole in your hand. Okay, you have a short pole in your hand, and you keep balancing until you somehow learn to balance the pole in your hand. Okay, you go through some trial and errors. You drop the pole, and ultimately you can, based on this trial and error, you keep on practicing, and you can balance a pole in your hand. Again, playing games. Initially you might be a beginner, but then you keep playing and playing and you become an expert in the game. Then there is a robot in a maze where the robot initially does not know which way to move, where to move, and everything. But ultimately, based on when it explores the whole maze, it can actually learn this policy that can ultimately lead go out of the maze in a shorter duration or something. Okay? I just want to show this short demonstration of reinforcement learning. Let me just. Is my screen visible? Is this video visible? Okay. So this is a very short demonstration of how reinforcement learning works. Okay. You see, ultimately the dogs want to get to this portion. Okay, so they can get some food. These dogs, go through different trials and errors. Okay, it goes here. Ultimately, you can see, some, try to go here, some fail, and ultimately each one learn from one another. Okay, and finally you can see. See, it learns how to cross this, and finally it gets to its foot. And then more and more learn from this dog, and keeps coming to the food plate here. Okay, uh, is all the four learning paradigms of machine learning clear? What is supervised learning? What is unsupervised learning? What is reinforcement learning? Everything. Is it clear? Any doubts? Hmm, Can I go ahead? ஏதாச்சும் doubt இருக்கா? Okay, no doubts. So again, these are some of the principle you have to follow while designing an ML system. First is choose the training experience, or you have to choose a data set. Okay, I want to choose exactly what it is to be learned, what I want to predict ultimately in the end. Okay, and so in the, let's say, MNIST data set case, the training experience will be all human labeled handwritten digits. Okay, I have the images, I have the labels. Okay, that will be my training experience. Choose exactly what it is to be learned means what I want to predict. Given the image, I want to predict what digit it belongs to, whether it's 0, 1, 2, 3, or 10, something. Okay, And how to represent the target function. How to represent the target function means which ML algorithm should I use to achieve that goal, and choose a learning algorithm. Learning algorithm means I have the model with me, I have the data set. How do I train that model to infer the target function? So that will be your learning algorithm. So these are the four main aspects of designing an ML system. And one thing you have to keep in mind is generally when we have a data set, we split it into training and test data set. Okay. So this will be a training experience or data set. Okay. You choose a model, it can be linear regression, lasso ridge, something, okay, neural network or anything. You choose a model, you train on this data. Okay. Ultimately, what I want to do is make predictions based on this data. Okay. Whenever we develop an ML system, okay, we have the training data set with us. But if you want to apply to the real world case, okay, it might not work. Most of the times that will be your case. I think a few years back, Google actually trained an ML model to detect diabetic retinopathy. Okay, you take pictures of your eyes, and the ML model can actually predict whether you have diabetic retinopathy or not. Okay, that is a condition where due to diabetes, your retina gets damaged, and ultimately you lose your eyesight. Okay, uh, but then again, when Google developed the model and deployed it, into clinics, the model actually gave wrong predictions. Okay, when consulted by a doctor, the doctor said you have diabetic retinopathy, but then the model was predicting you don't have diabetic retinopathy. Okay, so ultimately, whatever you do in house with the training data and whatever you deploy, that might be entirely different. Okay, so what you want to make sure is you have adequate test data. Test data is you get it from the real world. Okay, that is representative of all the cases. Okay? You train the model using training data alone. You don't show this data to the ML model. You only show the training data to the model. You get it trained and then apply it and check whether it actually works on. Okay? And this is how this is what data splitting means. You existing data set, you split it into train, you split it into test. Train the model using training data alone. Don't use test data, and then actually evaluate whether the model is good or not based on the test data. Okay. So in summary, there are tens of thousands of machine learning algorithms. I think each month, each year around 100 algorithms gets published in ML. It's hard to keep track of which algorithm to use for which problem and everything. But every ML algorithm has these three main components. One is representation. Representation, what kind of model I should use for what kind of task. That is your representation. Optimization is how do I combine the representation and the data set, okay, and make sure that the model actually learns these patterns from the training data. And evaluation, how good the model is. Okay, evaluation should only be done on test data. Okay, these are the three main components. And yeah, ML in practice, first you have to understand the domain. You have to make sure you have a clear goal. Once you have this goal in mind, you go around, search for data, you clean it, you do pre-processing to make sure it's standardized and everything, and you learn models. Once you try out different models, you get results. uh, Once you've tried all the models and you have interpreted all the results, you consolidate everything, and then again you keep refining this step by step. This goes on in a loop. Okay, that's what ML in practice actually is. There is no one single ML algorithm that can work everywhere. You have to try different methods of data selection, cleaning, different models, and everything, and make sure you have a comprehensive evaluation suite. Okay. Uh, okay. Any doubts till now? Uh, ஏதாச்சும் திரும்ப எக்ஸ்பிளைன் பண்ணணுமா? ஏதாச்சும் புரியலன்னா கேட்கலாம். Doubts? Okay. No doubts. Good. Okay. ML system design, different types of ML லாம் பார்த்தாச்சு. Now we are moving on to the first paradigm, supervised learning. That to the regression case first. Okay. Regression problemல you have an outcome or response variable y. Okay. Then you have predictor variables. You have the output, you have your input. Okay. X என்றது they typically call features. ML community they call it features. Okay. Then you have to have a question about y. How to predict y under different conditions? What model should I use so that as the inputs change, how is my y affected? Y வந்துட்டு we call it dependent variable, x என்றது independent variable. Okay. Y y என்றது why do you call this output outcome as dependent variable is whenever you change the input, the output also changes accordingly. So that's why it's dependent. And x என்றது you get the measurements. Uh, let's say do you if you want to check diabetes progression, x can have the age, you can have your BMI, blood glucose level, அதெல்லாம் it can be input variables. Y என்றது how much diabetes progression you have. That is one example. Okay. Can anyone suggest a case where you have a single outcome and multiple independent variables? Any examples? Let's say stock price prediction itself. What will be your output and what all can be taken as input? Or disaster prediction also. What is your output and what can be your independent or input variables? Mhm. You can use ChatGPT and also answer. Anything is fine. I just want what can be an outcome or output and what can be my input for a specific task. Any idea? புரியலனா I can explain again. Hmm. Okay. What do you mean by historical earthquake records? I want anything specific. Like historical earthquake records means it can be readings from a sensor. Okay. It can be the temperature at that specific day. It can be how much rain, you know, that has happened in a specific day. The independent variables, should have some type of relation which should be with the output. Okay, you can't take in random independent variables and you know put it into your model and say like this has a relation with the output variable or something. Okay, it should be specific to your domain. Okay, and yeah, this is a good example. Okay, moving on to univariate regression. Univariate regression now I have a single predictor variable, okay, and a single outcome, okay. And see, this is my independent variable, this is the dependent variable, and these are some data points I have. What I ultimately want to do in the case of linear univariate regression is I want to get this line, okay. I want to get this line, and so this is an equation for the line, okay, where beta naught and beta 1 y is equal to mx plus c martha. So here, which is my slope and which is my intercept? And y again should be continuous, discrete or இருக்கக்கூடாது. Not like success or failure. It should be some continuous outcome. Straight line equation இது. I have beta 1. This is my slope. எப்படி இந்த line வந்து how much it can, you know, this that determines the angle, okay, of this line that it makes the x-axis, and beta naught is where it intercepts this particular axis. Okay, that is my intercept. And our task is to find this line. If I want to find this line, I want to find beta 1 and beta naught. Okay. That is our ultimate task in the case of univariate regression. Okay. Again, I assume that there is a linear relationship between the independent variable and the dependent variable. Linear relationship na, as x increases by some amount, y also should increase by some amount in that same specific direction based on the slope. So that is what I call a linear relationship. And so the resulting model that you have, okay, y cap is the predicted value, beta naught cap and beta 1 cap. You estimated from data. Okay, based on data, you calculate beta 1 and beta naught. Again, while doing the coding session, I'll explain how to get these two parameters. Okay, and here our objective should be minimize this distance, as you can see from this point to this line. Okay, I want to find a line such that minimizes this distance. Uh, so if you see from this plot, if I draw a line here, all the points are very far off from the line, and that is not a very good model, I would say. Okay, I want the line to be somewhere in between these points, that most of the points may fall on this line. Whichever points are not on this line has the minimum distance, this point to this line. This should be as much close as possible. Okay, that should be our objective. Why is this key objective means if again a new data point, let's say TV comes into picture, the line, if it falls on this line, the predicted value, that might be a very good, I would say, fit. Okay, that might be a very good prediction. Okay, and how do I evaluate whether this model is actually good or not? Okay, I use something called the mean squared error. Again, this is the same, the distance between this point to this line, the vertical distance. Okay, I want it as less, as low as possible. Okay, if I want to find a good model. But again, as you can see from this diagram, all of them have the same mean squared error, the minimum mean squared error. Which one do you think is the best fit here among these four? Which do you think is a better model? Which is a good model? All of them have the same no distance from that vertical distance from that line. Okay, but which one do you think is a better model, or is this concept not clear? Just by looking at it, how, what can you say? Which is a better model? Just say which do you think? Just by looking at it, which can you say? Which model is a better fit? Model means I represent. I mean this line. Okay, it's this model. Okay. Here the problem here is there is no linear relationship. As you can see, there is some kind of linear relationship that can be, you can use a straight line to define that relationship, I would say. But here, if a model has a line that actually goes through these points like this, don't you think that would be a better fit? Yes, no? So again, there are problems with these. Again, a line can be like this instead of like this, that has the minimum MSC. And yeah, and this is like an outlier or something. And yeah, we'll talk about outliers later. But yeah, this is a pretty good model, I would say. It passes through most of these points, and the points away from the line are as close as possible. Okay, this is a good model. Okay, this is how you visually look at it, and it just don't go by this mean squared error metric alone. Okay, and the next case here is, as I told you before, here a linear relationship won't work. I want a non-linear relationship. Okay, so again, that's where this polynomial regression comes into place. Univariate case, you have the model only till here. This is univariate case. You have a single input and single output. But what if I have multiple inputs, say x1, x2 till xn? Okay, I want to utilize all the inputs to arrive at a single output. That's where the multivariate regression case here. Okay. So as you can see here, this is the multivariate regression case in 3D. Okay. X-axis represents how much radios you have. This Y-axis represents how much TVs you have in stock, and this Z-axis represents the sales, how much sales you'll be doing. Okay. This is the multivariate regression case. But if you look at the polynomial regression case here, you only have a single feature. But here I square the terms. Here I can put it up to degree n. Okay. Uh, so this is the linear regression case. Okay, just a straight line. And if you have data like this, if I expand it to degree 3, okay, I get a curve like this. Okay. And if I extend it to degree 20, okay, this n till 20, I get a curve like this that goes through every point in the training data set. In this case, which do you think is a better model? Should it be degree 1, degree 3, degree 20? Again, go back to those principles before. Most of the points should fall on the line, and that those that does not fall on the line should be as close as possible. This vertical distance. Remember, train data set, test data set. Just think about in this case. Tell me which is the best model that you can do. Mhm. Is it model 1, model 2, or model 3? Am I audible? Hello? Okay, I'm audible. Uh, can any of the participants answer this question so that I can know for sure that you all understood the concept? Which one do you think is better? Just look at it. Anything you answer is fine. I can give an explanation of why it works or why it does not work. Just model 1, 2, or 3. Or you can raise hands. How many think first model is the better model? Hmm. Okay. So the answer here is the second one is the best one. Okay. Second one is the best because here there is no linear relationship. Okay. Here the line goes through most of the points, and here the line goes through all of the points. Yeah. And so again, as I told in that example from Google, So this is the training data set. Okay, you don't want the model to overfit to the training data set. You don't want a model that goes through all the points in the training data set, because in the test data set you might have some points here, you might have some points here. So ultimately, what matters is the test mean squared error. Okay, so you don't want to overfit to the training data set. You don't want underfitting also. So this is the underfitting case where the model is not good at all. Here is the overfitting case where the model is too good on the training data set. Here I would say is the correct fit where both the training and test error might be as minimum as possible. Okay? To explain this, there is something called the bias and variance trade-off. So here, so this the y-axis has the error. This is the test error, and this is the train error. And this is the model flexibility. Here, flexibility increasing the number of features. The training error is as low as possible. Okay, as you keep increasing the number of degrees. But here you can see what happens to the test error. Okay, ultimately, initially it was here, keeps on reducing. It reaches a minimum, and if you keep increasing the model flexibility, again the test error goes up. Okay? So here, this point, here this corresponds to degree 5. Okay, is the ideal model flexibility. Okay, you don't want to, this is the overfitting case and this is the underfitting case, and here is what you get is the correct fit. Okay, uh, and this is the bias and variance trade-off. Okay, and yeah, here is the point where you have the lowest possible test error. You should only look at test error, not the training error. Okay, you want the test error to be as minimum as possible. That's the takeaway here. Okay? And how do we prevent overfit? As I mentioned before, reduce the number of features. You have to manually select which feature is most important for your particular case. Okay, you can manually set, or there is something called the model selection algorithm, where there are different techniques. There is like forward selection, backward selection, and other stuff. Okay, we won't be going into details about model selection algorithm, but we'll be looking at regularization. Okay, regularization means you keep, in the case of ridge regression, these are different types of formulations you have for uh, regularizations you have for the linear regression case. Okay, regularization, you keep all the features. Features means the independent variables or input, but reduce the magnitude or value of the parameter. Parameters being your betas. Okay, that is one type of regularization, so that you can make sure that not one specific feature has most of the importance towards that output variable. Then there is something called lasso, or what you can do is variable selection, where you put some of the parameter values to be zeros. Okay, that's where your variable selection comes into picture here. Okay, I think that will be the lecture for today. I think the last few slides might be they might be a bit overwhelming, but I think if you go through the coding notebook that I'll be sharing now, it would be become slightly easier, I guess so. Uh, so, any questions before I move on to the coding session? Anything you can think of. தமிழ்ல கூட கேட்கலாம், பிரச்சனை இல்லை. no. It's not about optimization. It's about which features um, are most important or contributing to that particular outcome. Okay. Um, so let's say I have 100 features, 100 input variables, a single outcome variable. All of those features might not be contributing to that specific outcome. Okay. So I want to select which are the most important features. So that's where model selection comes into picture. One example technique is you keep, so you first you start with the bigger model. Okay. You train a linear regression model. Okay. So this is you start with all the 100 features. Okay. You keep removing features one by one. Okay. So let's say in the initial model you have 100 features. You remove one feature, you have 99 features, and see how the test error changes. Okay. If the test error doesn't change much, you can drop that feature. So it's like you keep on removing one by one and finally arrive at a specific subset of features where the test error doesn't change that much. That's it. Okay, maybe I'll share the notebook now. Just so I have uploaded the notebook in this drive folder. You can all use Collab. You can upload it to Collab, open it in Collab, and I've set the notebook in such a way that it's like fill in the blanks. Okay, where for each variable you have to assign a value, and the code executes when everything is correct. Okay? Um, just try to execute that notebook, and if you have any doubts, let me know. I have not included lasso and ridge regression in the notebook now. Also polynomial regression also. Uh, you have to download and upload it to Collab. Mm, so Collab. You have to go to this website and upload it. Yeah. I see the code is only for the linear regression case here. Uh, I'll upload the rest by tonight. Again, if I've given all the formulas, everything in the notebook. You can just see and make sure you fill in at the right places, okay, so that you can get the output properly. Also, I have included a short feedback form for this tutorial in the chat. It would be helpful if you all can fill that so that I can refine the next set of lectures based on the response. I'll be here till 7 if you all have any doubts. Uh, you can try this notebook and maybe tomorrow I'll start with the solutions so that it's easier for you all to understand.